All right, so when we start looking at this, if we go ahead and use direct substitution, we get 1 plus some constant over infinity. This leads to 0 to infinity, so all of this equals to 1 to the infinity power. And this is indeterminate. So we have to go ahead and look at it a different way. So we now want to write this as y is equal to the limit as x approaches infinity of 1 plus some constant over x raised to the x. And now we're going to use this idea of taking the natural log of both sides. So on the left, we just have the natural log of y. Now, what we're going to do with this other part is take and move the limit on the outside and move the natural log on the inside of 1 plus cx over x. Now, why can we go ahead and do that? Because we have this rule with functions and limits that says if you have the function of a limit as x approaches some value of g of x, as long as that function is continuous, which the natural log is continuous, that is equal to the limit as x approaches a of f of g of x. And we are doing this for this case of the natural log, right? And we can do this because the natural log is a continuous function. So that's why we're allowed to do this, and that part's really important. All right, so once I have that, I'm looking at bringing the x from the exponent and bringing that in front. So now I have the limit of x times the natural log of 1 plus c over x. All right, so what happens here is the limit of x goes to infinity. This is of the indeterminate form, and the indeterminate form that I have here is infinity times direct substitution inside here will lead you with 0. And that's because c of x when x goes to infinity is 0, leaving you with a natural log of 1, and the natural log of 1 is 0. Now, we can't use L'Hopital's rule with this. We have to do a little kind of work with that. And there's a little trick we can go ahead and use with this idea of x to get this in the form of 0 over 0, so we can use L'Hopital's rule. So what we're going to do with this x is we're going to change it to, let's just write this out. This is the limit as x goes to infinity, and I'm going to make that negative x to the negative 1 to the negative 1. And what that's going to allow me to do is put that in the denominator. So that's times the natural log of 1 plus some constant over x. So now I can rewrite this whole thing as the limit as x approaches infinity of the numerator is the natural log of 1 plus my constant over x, and my denominator is that 1 over x. And again, it's a little strange, but what I'm saying is x to the negative 1, which is my 1 over x, and then it's to the negative 1 power, which drops it in the denominator. All I'm saying is I want to get this in the form so I can use L'Hopital's rule, which I can, because now if I go through and use direct substitution in the denominator, that 1 over infinity is going to give me 0, and this is 1 plus, again, my constant over x will go to 0, and the natural log of 1 is 0. So now it's in L'Hopital's room form, which is 0 over 0. So I just have to find the derivative of the numerator and the derivative of the denominator. So for the derivative of the numerator, I have the natural log of 1 plus c of x. Now, for that, the derivative of the natural log, that is just u prime over u. So that gives me negative c over x squared divided by 1 plus c over x. Now for the derivative of the denominator, that's just 1 over x. Remember, this is just the power rule. Bring the x up, x is negative 1, subtract 1, bring the negative 1 out front and subtract another 1, which gives us negative 1 over x squared. All right, let's go ahead and put this all together. And at this point, when I'm putting it all together, I do want to go ahead and take a second and remember at the very, very beginning what we said this was equal to. This was equal to the natural log of y. So the natural log of y is equal to the limit as x approaches infinity of negative c over x squared all over 1 plus c over x, and that all gets divided by negative 1 over x squared, and this cancels out, becomes positive, and all of this is now equal to the limit as x approaches infinity of c over 1 plus c over x. All right, direct substitution works with this. When I go through and put in direct substitution, I go ahead and I'm left with my constant, 1 plus c over infinity. C over infinity goes to 0. So all of this is just equal to c over 1, or just c, which is beautiful because now we are almost done. Now we have that we know the natural log of y is equal to c. And as a reminder, just what we're trying to do is we're trying to get y all by itself, because our original what we started with originally was the fact that we want to let y equal the limit as x approaches infinity of 1 plus c over x raised to the x. This was our original question. So by solving for y now, we can have that answer of what does the limit of 1 plus c over x always equal to. So this, what I just put down here, is this is just a reminder of what our original question was. We set this up so y is equal to our entire limit. So we do have to go through and finish solving for y. And then we're going to have a value where I know this limit is always going to be equal to. Now, how do I do that? Well, I do that because I know that this is just base e, right? So I change this to exponential form, and I get that I know that e to the c power is equal to y, or in this case, any value e to the c is always going to equal the limit as x approaches infinity of 1 plus c over x raised to the x. And this is a really useful limit to have memorized.